Imagine you're an archer in a magical forest where every tree is a data tree. Each tree holds information, leaves are features, its branches are patterns, its roots are the foundation of knowledge. Your goal as an archer is to hit a target image hanging in the distance, an image that represents the perfect outcome, like a prediction. But first, you need to craft and train your bow. Initial bow, untrained model. When you first pick up the bow, it's raw and unpolished. You can shoot arrows, but they won't fly accurately. Training process, learning algorithm. As you practice, you refine the bow's string tension and data noise. This is equivalent to adjusting the model's parameters during training. Leaves, features. Each leaf has unique details, like the size, color, or texture. These are the variables or attributes the model learns from. Branches, patterns. Branches connect leaves and represent relationships or patterns in the data. Roots, foundations. The roots ground the tree, just like foundational principles anchor the dataset. Once your bow is trained, you shoot arrows at the target. Each arrow is a prediction. Your aim improves as you learn more about the tree and its patterns. Producing the target image. After several iterations of shooting, training and validation, your arrows hit closer to the target. Eventually, you produce an image, a visual representation of your trained model's predictions or output. It might be a classified photo, a generated artwork, or a reconstructed object. In essence, machine learning is like mastering archery with magical bows and data trees. The better you understand the tree and train your bow, the closer your arrows land to the perfect image. Visual metaphor. The tree is dense with leaves and tiny branches, overly complex, but impractical for understanding the big picture. Imagine the tree grows excessively detailed branches. Every small branch and leaf tries to represent specific details of the training data perfectly. The glowing neural connections in the tree become tangled, overemphasizing minor patterns, noise, in the data rather than general trends. This is called overfitting. Visual metaphor. The tree is sparse, with only a few branches and leaves, unable to represent the richness of the data. The tree doesn't grow enough branches or leaves, and its structure remains overly basic. It misses important patterns in the data. The glowing neural networks are weak or sparse, failing to capture the deeper connections within the dataset. This is called underfitting. Striking the right balance. A well-trained tree. The ideal tree grows just enough branches and leaves to represent the important patterns in the data. It's neither too complex, overfitting, nor too simple, underfitting. The glowing neural network connections are well structured, efficiently capturing meaningful relationships without overburdening the system. In machine learning, achieving this balance involves techniques like regularization, cross-validation, and early stopping, which ensure the model generalizes well without being too rigid or too simplistic.